Okay, class, welcome. This is weekly update. What are we up to? Maybe like 6 now? So you guys just finished week 1 of module 3. So we did local extrema, saddle point CPs, determining what the D tests, which of those might be max, which are min, which are saddle points, and some really nice assignments. And then you also did a tech tools discussion. So I just want to do a few shout outs. Let's see, first thing, maybe I'll start with announcements actually. So announcements, I put a practice midterm at the end of module 3. It's optional. You don't have to submit it. You don't do it if you want. You know, if you did it, you think you did a nice job and it would help your classmates, it would be nice. Email it to me and I'll post it for the class. But I think it's good for everyone just to print it and take a look at it to see where you're at. Those are the level of calculation problems that you would see. Our final exam, though, will have calculation and concept. And I think you've got plenty of practice with the concepts from the activities, from the quizzes, from the concept questions at the end. And so this was just to give you a sense of the level of difficulty of the calculation problems that you're going to face on the final, where you have to show your work. So print that out, take a look, and if you got questions, just send me an email. We'll do another office hour. Thank you to Nia for suggesting another office hour, and folks that showed up, so Brianna and Lainey and Brianna. So thanks for those questions. However, I forgot to record that while we were there, but I think many of the questions were the same one that Lucas also emailed about, which was finding critical points. You know how to, once you have your critical points, to do the D test and determine local max, local min, or saddle point. It was just finding those critical points was a challenge sometimes. So I worked a few of those and put it in a critical point review video in, let's see, week 2 of module 3. So check that out. And then folks also on the last module had a lot of questions about directional derivatives. So I also put another review video there. So I sent an email also, check that out with the links, or just go into your OAKS content. Okay, so you're starting now the last section of chapter 3, which is global extrema and optimization, and you're getting ready for challenge problems. So I think it's always a good idea at this point in the module to go ahead and read that challenge problem a couple times. Decide, it helps motivate you for what's coming up in your journal. And so, you know, when you're reading about global extrema, you're constantly thinking, like, could this help me with the challenge problem 4 or 5? Could this help with the one I think my group wants to do? And I think you'll find these are also very practical and interesting challenges, and challenge yourself. If you've got time and interest, go for some more upgrades. Okay, so let's see, next comments. Local extrema activities, there are some really good ones. I'm going to put these in the samples and examples of this week's OAKS module, week 2. So let's see, I think some really nice ones are for the hand under the shirt activity, and just visualizing local extrema and saddle points. Some nice visualizations were done by Sam and Joe. They both took, rather than shirt, they took a picture of a surface, like put a fabric over something, made some points, and labeled them all. It was easy to see, so I'll put those in there. I really liked the discussion that, I think it was Kyra and Brianna, for the one about eyeballing local extrema. You had in your journal just a 2D graph of something, and you know, I think Kyra's comment was kind of like, hey, this is really hard to do, right? I can't find that missing, I think the missing one was a saddle point. You know, how am I going to find that given this just 2D thing? And Brianna then took it a step further and was like, well, let me go ahead. I have the explicit equation of that surface, so let me go ahead and put that in Calc-Plot3D and like rotate the view and see if I can find them. And even at that, it's still hard. And I think that reminds me of Jenna made a comment, and she did a really nice video. I'm going to post that as well for 3 or 4 of the activities that she discussed. Short 5 minutes, but you'll really get a lot out of them. I think she hits a lot of highlights. Great job explaining. But yeah, she made the point that, like, that's the whole thing. Eyeball estimates, even in the 2D, of course, but even in the 3D, can be deceiving. And that's what's so nice about the calculus, is you have this objective way of scientifically arriving at what are these CPs. Okay, oh, the crumpled paper activity, several of you did this, a really nice job on Ellie, so I'm going to post her. She has a very nice description of her sort of thought process throughout that. I think Eddie did a nice one too. Let's see. But so many of you talked, so in that one, you took a piece of paper, crumpled it, and uncrumpled it, and now you had a surface. And this surface was definitely not smooth, and that's okay. I mean, this is more real life, so it had a lot of jagged points, so a lot of non-differentiable points. And you were asked to drop liquid and watch it follow the path of steepest descent, right? So that's a raindrop lands on this surface and at different places. And then the question was something about, well, could you create an algorithm that will help you find these CPs or local min? And many people talked about, basically their algorithm was something very similar, like programming the algorithm to do what you as a human are doing by, okay, well, I'll make it solve the f of x equals 0, f of y equals 0 equations. I will then, so then I'll have some CPs, and then I'll make it through the d-test. And that's true. So this is programmable. That's how basically when you just ask Wolfram Alpha for the critical points, it's doing something like that. And by the way, Mathematica is actually the background behind that, which was invented by Stephen Wolfram. But because that mathematical language is so difficult with the syntax and everything, he tried to make a natural language like layer over top of that, Wolfram Alpha. But I guess one of the ideas I didn't see anybody talk about that I was hoping to see is, rather than making use a computer to do something that it's good at that maybe you're not good at. And this is the neat part when you start thinking about, you know, how do we merge these? Like, humans are good at a certain type of thinking and computers are good at a certain type of thinking. And they have places that intersect and overlap, but then there's places that are unique to each of them. And so one thing I think would be needed, there is an algorithm called the steepest descent, or if it's steepest descent, it's called the hill climber. And what you can imagine is we have a surface, you know, we have some surface, and we want to drop, instead of raindrops, imagine dropping little parachutists down over a grid, right? So we can drop them in a very specific, uniform way in this grid, and they're all going to come down and land relatively in a grid on this. And then we have them, if it's the hill climber and we're doing ascent, you just say, take out your gradient compass, you know, see where it points you, and start walking in that direction of 3 steps. And then use that gradient compass again. It might redirect you slightly, walk another 3 steps, and keep on going. So you can program that if you have an explicit expression of the surface. So if you have a z equals f of xy, or in n dimensions, and then you're dropping a bunch of these parachutists, and you just tell it to walk in the direction of steepest descent, for our example, where we're trying to get the mins, if you want to get the maxes. And if you do it with enough of these parachutists that come down, and the computer would love to do, send it 1,000 parachutists over a very finely, a very fine mesh grid over top of that surface. They'll land, they'll each compute the gradient at that point, they'll each take some small number of steps and moves, they'll recompute, and then at some point, some of these parachutists are converging to a max over here, and some of them are converging to a max over there. And if you just do that enough times, and there's no guarantee that you'd find all those max, or if they're going down, all those min, but it's a very easy algorithm to program. And if you took 245 or take some graduate classes with me, we'd learn more about these optimization algorithms that use the computer to do what it's good at and use the human to do what it's good at. Okay, so that was the, oh, and that actually sort of ties into, actually one more point. So then the d-test practice, some really nice work where people laid out all their step-by-step and sort of thought process. So Kyra, Eddie, Ellie, Christian, Michael, Joe, Charles. So I'm going to put all those in there. And what I specifically liked about Charles is in his, he was saying like, hey, I actually got this as my result, but then I went over here and checked it with CalcPlot3D and it's inconsistent. So I'm trying to like work out, you know, was it something I entered in CalcPlot3D, or is it something I'm doing with my partials? And in some cases he didn't resolve that, but I just really appreciated seeing his thought process of what was happening in each step, and it was just perfectly in line with what you should be doing when you write these problems. Okay, and then the last thing was the tech tools discussion. That was another assignment. That was really fun to read through. Many of you, it was good to see that many of you were like, hey, I don't just jump to the, I do not just jump to a tech tool. I try to work the problem by hand, and then I'll use CalcPlot3 to see if that verifies, or I'll go to Wolfram Alpha and ask it for it to do the critical points. I think that's great strategy. And really what I intended though with this problem, and I'll probably try to be more specific in the future with it, was using a tech tool for something you can't do by hand. And we've only seen a few instances of that this semester, but you'll see more in your career, and especially in your job when you go out and if you're working for a government lab. I mean, you're not sitting down doing most of these things by hand. You're getting the models and the intuition, and then there's going to be something where you're using a computer-assisted method to do it. And one example, though, that we have seen is critical points, finding critical points when the f sub x equals 0 and f sub y equals 0 equations are so intertwined and tangled that it's really hard to separate them. And so you can use a tech tool straight away to do that, and you get, oh, okay, it says the critical point is like at x equals 3, y equals 5. Well, you know, how do you check that? Well, it's very easy in that case because we know what it means to check, what it means to be a solution to those equations. But in some cases, it's even harder. So I just wanted to mention a few folks' answers that I liked, and then we'll talk a little bit, maybe go off on a little historical tangent. So Brianna Pope wrote a nice thing about, like, she has a reasonable range of values. Like if she's getting I's, then, and we're not in a complex numbers class, I'm not doing a complex analysis, then that's a clue, right? Joe also talked about you should have that estimate before you go to the tech tool. Otherwise, the tech tool can kind of bias your understanding of what's happening if you're trusting it too much. So again, good to see that most of you are like, I work things out by hand. In many cases in our class, you can. I also really liked Lucas's answer about, like, hey, it's just think about what you get when you're done. Does that even make any sense? And then he also mentioned the fact that sometimes it's human error inputting it into the computer. So he'll try, like, on a totally much simpler problem. Like maybe he's trying to do a double integral, but hey, let me just do this really simple integral, single integral. Like, what's the integral of x squared, you know, from 0 to 4? Well, I know what that answer is, and then I'll check, like, if I extrapolate that and try to do that same sort of syntax or whatever in the double integral, am I getting something that makes sense? So trying a simpler problem. I also like Corbin's way. He talked about, like, sometimes if you're working on a higher dimensional problem, can you knock it down a dimension and ask the tech tool to do that easier one? And then you have some intuition about that problem. And many people, I thought this was interesting too, verifying tech tools with other tech tools. So, like, because, and maybe that's again back to the sort of the syntax issue, knowing, again, Mathematica syntax is much more difficult than a TI calculator. Things are meant to be user-friendly, but then that user-friendliness usually comes at a cost, and the power of something in Mathematica, well, once you get to be a good Mathematica user, you appreciate those syntax. They seem a barrier down here, but they're useful later. Let's see. Yes, okay, so again, hopefully we'll have some tougher problems too, where you'll see, like, you can't even work this thing by hand, and you're gonna need to rely on a tool, and how do you know whether that's accurate and what's happening? And it helps to know, also kind of know what's happening behind the scenes, even if you don't specifically know Newton's method or method of gradient descent that is solving this system of equations. It's good though to have a key and then maybe Google on that, or take numerical methods, 245, 545, 445. We have multiple ones. Those are really neat ways of seeing how many of these complex things get solved. That you could do the small ones, you could do Newton's method by hand, but again, it's something the computer appreciates doing. Oh, and then to say that, also say that historically, this is really kind of interesting too, because Newton and Leibniz co-invented calculus independently, and Leibniz's goal was, he was really hoping that, and I think he wrote a paper, something in the title where it was like, he was hoping that calculus would be so mechanical that he was basically saying, hey, look, my methods of calculus make this so mechanical, you don't even have to think about or understand what you're doing, and you're getting an answer that the engineers can use to build a bridge, right? So if we need to know something about center of mass or volume, and you're doing an integral, and he was saying, like, the value of his methods was that you can just crank away and give it to someone to basically be a human calculator. He also had this dream about universal computation and sort of systematization of human thought. And one thing that's interesting too about Leibniz is he was working on he spent his entire life working on a calculator. He was hoping, like, making his own little TI, I guess. And addition, subtraction, multiplication. So he was sort of obsessed with this mechanizing of computation idea. So, and he made one, he spent, I think in his lifetime would have been over $1 million trying to make these different models and getting some funding from governments and princes and municipalities. And he made a little wooden prototype, and it was called the reckoner, the stepped reckoner. So I love that name because it reminds me of like it could be like a WWE character, like WWF, like the reckoner. Anyway, this thing was made out of wood. He had wooden gears in there, and that was the prototype for what would be a mechanical one. But what was really cool was he had this crank on the side. So multiplication, you'd kind of crank forward, and if you wanted to divide, 4,195 by 7, you'd go this way. If you want to multiply those two numbers, you go forward. Which was also just another historical tangent, was why he was able to get credit for calculus. Many people had done sort of the derivative side before, and many people had done the integration side, but they hadn't linked them. Newton was the first, Newton and Leibniz independently, again, first to make that linkage, that those were inverse operations. One does something, the other one does it. And for Newton, it really makes sense because he spent his life thinking about this calculator and inverse operations like addition, subtraction, multiplication, division, using ln, squaring, square rooting, and all with this like physical crank. And so like derivatives come this way and anti-derivatives go the other way. So check it out, just Google that on the step reckoner. It's pretty neat to see one of the first calculators. Okay, I think that was it. So check out the, I'm gonna post some of these examples in the samples and examples section, and then we'll, and check out the midterm. Have fun with this week and the challenge problems. Good job last week.